And I'm recording at 6 o'clock or 6:01 on July 12th, 2018. This is the regularly scheduled lecture of ITSE 2309 at Collin College. Today we're going to be talking about Module 10. Module 10. And let's see, I believe this is Chapter 8 in the textbook. Modules. Module 10, Data Types, Chapter 8, and I'm going to begin with, let's see, look at the introduction, and here is this isn't Dr. King's lesson, but this gives you another take on it besides me. And so data types fall into four fundamental characters, and basically we have string, it's either string or character data, and then we have numeric data type, which is integers, floating point numbers, currency, other floating fixed point numbers, temporal dates and times. So the ones that we consider the most interesting are the top three. And the bottom one is what we in computer science call blobs. And this is binary large objects. Now, blobs are not particularly exciting to us. A blob is just a big something that's in the database, and it's treated just as a binary object. It could be a picture, it could be a digitized fingerprint, it could be a song. I once had a student that did a project on blobs where he stored all of his movies in a database as a binary large object. But by and large, we're not particularly excited about them because we can't search on them. Let's start with the numeric. I'm going to start immediately with the idea of the integer. Okay, computer programming, integers are integers. There are two decisions that we have to have in here, and that the first one is, does the integer have to have both positive and negative numbers in it, or is it just a absolute value? In other words, is it unsigned? Secondly, how much storage will we have to allocate for each integer? And we find that 4 bytes is the most common for an integer. If the integer is unsigned, if it doesn't have a positive and a negative associated with it, the integer is simply stored in base 2. That's about it. And the maximum value that we can represent is 2 to the number of bits power. For example, if we have 8 bits in our integer, the maximum value we can represent would be 2 to the 8th power. And if we were to work that out, we would get 1, 2, 4, 8, 2 to the 3rd power, to the 4th power, 16, 32, 64, 128, 64, 128 different bits. That would be 2 to the 1, 2, 4, 8, 16, 32, 64, 128 different bits, different numbers. So we can store up to 2 to the 8th power minus 1, or 255 different values. Okay, so if we used a 1 byte, all we've got is 255 different values. And if we store it as a type tiny int, that would be one of these values. If we had a 4-byte integer, we'd be able to store up something like 4 billion, 2 to the 32nd minus 1. Our data types that we have to work with, let's see. Okay, let me go ahead and cover signed integers. And if we think of signed integers, Anytime there is a sign involved, we have to use one of those bits as a sign bit. So we lose half of our range, because if I take one bit away from a byte, for example, if I have an 8-bit integer and I have to use one of the bits to represent a sign, I only have 128 possible numbers. I have positive 128 and negative 128. Now, if you want to take a look at this tutorial, it's pretty good, this particular one. Let me talk a little bit about these signed numbers. Half of them are positive and half of them are negative. Now, I'm going to drop over here for just a second, and I'm going to talk about this. Suppose we had 3 bits, and we start at 0, and we start going up. And up goes 1 and 2 and 3. Now, if this were a speedometer or something, an old mechanical speedometer, and I started driving backwards from 0, what would be the first number I would see? First number I would see would be a 7, because that's 0. When I go backwards, I'm going to see this one, and we're going to call that one -1. When I go backwards another, I guess it'd be a mile, I would come to a 6, and that would be a -2. And then I would come to a 5, that would be a -3. And then lastly, I'd come to a 4. And if I kept going backwards, I'd come to a 3. So you look at it this way. Think of this thing as a circle. If I go up 0, 1, 2, 3, my next number will be this one, 4, 5, 6, 7. If I go backwards 0, -1, -2, -3, -4. If I go backwards one more unit, I will roll around and get to this number. And this is what we call the 2's complement method. Now, notice that in this guy, there is always one more negative number than there are positive numbers. So the biggest positive number I can represent is a 3, but the biggest negative number I can represent is a -4. And the reason we like this is known as 2's complement. The reason we like this is because we don't have 2 ways to represent 0. If I just said, okay, the first bit, the leading bit, is the sign bit, and then the sign magnitude, so here's the sign, that's 0 is positive. Let's see if I can highlight it there for us. I think I can. Yes, the 0, it would be positive, and the 1 would be a negative. So this would say 0, that's 1 and 2 and 3. And so if I went the other way, I would have 1, 0, 1, 1, 1, 0, 1, 1, 1, and that would represent -1, -2, -3. And the problem with this is that I would have 2 ways of representing 0. I would have a positive 0 and a negative 0. And this would really just throw a hitch in the get-along of that. So we go to this method, which is known as the 2's complement, and thus we have only one way to represent 0, and that's 0. And then we have -1, -2, -3, and -4. If I add 1 to it, I come up with a +3. If I add 1 to a +3, I come up with a -4. And this takes me back to my next idea. If we think of going 1 degree west as -1 and 1 degree east of -2, notice that the greatest positive number is 1 integer away from the greatest negative number. So there's an old trick question that I always ask in my programming classes. I say, what state in the United States is the farthest east? And I get a number of guesses, and somebody will say, well, I think it's Maine or Vermont, or not Vermont, one of the coastal, Massachusetts, out on the Capes. No, I don't know. How about Key West? is out there. It's pretty far east. And so, but the state that is farthest east turns out to be Alaska. And the reason for that is that Alaska, the Aleutian Islands, if you look at a map, the Aleutian Islands actually extend into the eastern hemisphere. So the farthest east as you can go, if you go as far west as you can, you end up east. And it works that way with integers. If you go as far positive as you can go, add 1 to it, and you end up with a negative value. And that is so. It just happens. And the good thing about that's the property known as overflow. And I talk about it right down here. All integers represented on any mechanical device will eventually overflow. Now, you guys, I don't know whether you guys remember this or not, but years ago, automotive speedometers would overflow at 99,999 miles. I'm not getting a very clear, when I try to select, my mouse isn't working. They would overflow at 100,000 miles. When you hit 100,000, what would happen? Well, it would carry out of range. And when it carried out of range, you ended up with 0. It looked as if it was 0, and that was overflow. So when the automotive speedometer hit 100,000 miles, it showed you a 0 because there were only 5 digits, and that was all they could do. Now there are digital devices. It's much cheaper just to add bits. What happens when you get to the end of the range? Well, it still overflows. Every integer represented on any electromechanical device will overflow. You run out of bits, you overflow, and it either shows you a 0, or in my other example up here, it shows you a -1. Value carries out of range. If it's signed, think of it as stepping from the western hemisphere into the eastern. And the greatest positive number, when you add 1 to the greatest positive number you can have, if it's a signed value, it becomes the greatest negative number you can have. All integers will overflow. That's just that's part of the deal. It just happens. And there's nothing you can do about it except detect it, because when you add 2 positive numbers and end up with a negative number, something has happened. Okay, let's look at how much storage do they take. There are 1, 2, 3, 4 different kinds of integers that we can have, and we can call it a big int. And that takes us from 2 to the 63rd power to negative 2 to the 63rd power up to 2 to the 63rd power -1. Remember that I pointed out that you will always have 1 fewer positive numbers than you have negative numbers. That's a really, really big number. I don't even know what that number is. I copied that off the internet someplace. Thousands, millions, billions, trillions, quintillions, septillions, sextillions. So that's 10 to the 6, 9. I don't know. I don't care what it is. It's got a name, but we don't really care. And the storage that it requires is 8 bytes. Now, you won't be using a big int very much unless you need something that's really, really big. That's 8 bytes. More commonly, we int. Int is 4 bytes, or that is 32 bytes total. And an int runs from -2 to the 31st power. Remember, that's 32 bytes, but it goes to the 31st power to positive 2 to the 31st power -1. So that's something like 2 billion and 147 million more. So that's usually plenty for what you probably want to do. Excuse me. On the other hand, maybe you don't need that big of a number. Maybe you want to go with a smaller number. Maybe 32,000 is big enough. Maybe you're talking about something like, oh, I don't know, the average person's monthly income or something like that. In that case, we can use a small int, which is 2 bytes, only uses 2 bytes, and therefore it doesn't use nearly as much memory. And that brings us from about a negative 32,768 to a positive 32,767. And again, these numbers aren't really important. It's important to remember that it uses 16 bits. Therefore, 2 to the 15th is the biggest negative number. 2 to the 15th minus 1 is the biggest positive number. Finally, we can store stuff as a tiny int. If we use the term tiny int, this is what we use in database when we want something that is a 0 or a 1, for example. I would use a tiny int. A tiny int is just 1 byte. A tiny int has no sign associated with it. It's just 0 through 255, and it's just a simple binary value that is 1 byte, 8 bits. So notice that as we move up from tiny to small, we double. Small to int, we double. From int to big int, we double. Questions? Any integer overflows. What happens if the value I have in my tiny int is 255 and I add 1 to it? Well, I have just overflowed. I cannot represent 255 in 8 bits. What would probably happen, I expect, is that I would show a 0 in that. So I would overflow to 0. What would happen if I were at 32,767 in a small int, added 1 to it? I expect I would end up with a negative value, the largest negative value. Questions, pausing. Don't have anybody here. Mr. Kazuka, are you still here? Saw you pop in a minute ago. Okay, anything with a fixed decimal is an integer. Anything with a fixed decimal is an integer. May I say that again? If you fix the decimal, it is an integer as far as database is concerned. When you lock down that decimal, for example, if you say money, I will never store money as 11 and 32 hundredths dollars. I will always store it as 1,132 cents. In other words, I'll shift that decimal out, and then when I show it to you, I will put the decimal back in. So I will always keep it as, so $17.23, I will store it as 1,723 cents. If I tried to convert that decimal to binary, I would end up with a non-terminating binary point, and I would ultimately have to round it. But anytime that I fix the point, it becomes an integer, and then I lose all of that issue of having to round it. It is just simply an integer. Whenever I talk about something that is a decimal or numeric, they are the same thing. So data type decimal and data type numeric are exactly the same thing. So when I say decimal 8,3, I have a number, or numeric. Numeric is the same. I think decimal is preferred now, but numeric is still used commonly. I'm getting a number that has 8 digits in it, 8 base 10 digits. 3 of these are always right of the decimal. Thus, I have a fixed decimal point. Therefore, I have an integer. How big is it? Well, it has 8 digits. That means it will contain 10 to the 8th power different numbers, or 1 million different numbers. If we look at that a logarithm, if I take a log 2 of that, we see that it will require 27 bits, because log 2 of 1 million is 27. And one more because of the sign, so I need 28 bits to represent that number. But I can't allocate 28 bits. That doesn't fall on a base 2 boundary. So I would go up to 32. I would allocate 4 bytes for this number. So I'm going to have 30. I'm going to have 4 billion different values for that number, because 4 bytes are going to get allocated. Money is always 8 bytes. Money always fixes the decimal place at 4 places, and yes, money is an integer. In summary, integers are limited by the number of bytes. Anytime we fix the decimal, it's an integer. All integers will overflow. What is overflow? There's your test question. Overflow happens when an integer carries out of range. Overflow happens on the high side of the integer. So, for example, when the speedometer in an older car, what happened when you hit 100,000 miles? The carry happened on the left side, on the high side. It carried out of range. It went from 99999 to 00000. The 1 was still there, but it just couldn't represent it, so it carried it out of range. And it says right here, that will be a test question. Pay particular attention to what is overflow. Floating point. Floating point, float, and also known as real. We don't like floating point. We'll do so floating point or float sometime. So the data type is known as float. And back in the old days, you could call it real, but I think float is the new way to call it. Floating point. We do not like floating point. We all do almost anything to get around a floating point. Consider some fractions and ask, do they terminate? So does 1/2 terminate? Does 1/3 terminate, or does it have an infinite remainder? So 1/3 has a remainder. 1/4 terminates in base 10. 1/5 terminates. 1/6 has a remainder. 1/7 has a remainder. 1/8 terminates. 1/9 terminates. 1/10 terminate. And what is the rule? How can I tell by looking at a fraction whether or not it will terminate? Well, if I have a fraction and I want to know, so here's a fraction, 1/80. Will it terminate? Well, that is 1 over, what is 80? 80 is 2 times 40. 40 is 2 times 20. 20 is 2 times 10. 10 is 2 times 5. So 80 is 2 times 2 times 2 times 2 times 5, or 2, 4, 8, 16 times 5. And we ask, is everything in there a factor of 10? Our base is 10. So if that is so, then everything in there will go evenly into 10. Therefore, 1/80, if you divide it out, it will terminate. And I can put that into my calculator. And I can say 1 divided by 80, and it's 0.0125. It terminates, it ends. Well, what if I have a number like 1 over 36. Well, that is 1 over 2 times 2, 36, 18, 2 times 9, times 3, times 3. Okay, 4 times 9 is 36. But 3 is not a factor of 10. Therefore, when I try to figure this out and I try to get a 1 divided by 36, I'm going to get a repeating decimal. And I will always do that. And the way you can tell, will you get a repeating decimal, is do you have any factors, prime factors in the denominator that are not factors of 10? Okay, now let's go back to the base 2. A floating point decimal must only have a power of 2 in the denominator. So if I talk about the floating point decimal, 0.2, so 2/100ths. If I talk, so what is this? This is 0.2. That's 2 divided by 100. Will not terminate, or excuse me, that's 2/10. Because 10 has a factor of 5, and 5 is not a factor in a 2. So what will terminate in base 2 is only numbers like 1/2, 1/4, 1/8, 1/16, 1/32. If I talk about something like 1 penny, won't terminate in base 2 because that's 1 over 100, and 100 has a factor of 5 in it. Therefore, it won't terminate. Floating points suffer from underflow. And underflow happens because we cannot represent an infinitely long number. Therefore, we have to chop it off someplace. So when I chop it off someplace, I have brought into the problem an error. As soon as I chop it off, and sooner or later, if I talk about a 0.2, that's 2 over 10. And when I convert that to binary, let me see if I can do that in my calculator. Do I have binary? I don't think I have it here. I don't think I have a base 2. As soon as I try to go to binary with a 0.2, I'm going to come up with an infinite binary point. Okay? So a underflow, so this is what's called underflow. When I finally have to chop that thing off, excuse me, and I introduce an error into it, I get underflow. Now, underflow is an error on the right-hand side. Underflow is an insidious error that's so tiny it's not considered important. So what is for example, if I talk about 1/3, well, 1/3 won't terminate in base 10. So what do you get? You get a 0.33333333333333333 until you finally get tired of talking. But when you do finally get tired, you're down to such a tiny number that it's not considered important. But if you could take a whole bunch of those and add them up, you would get an amount that is important. So the difference then, overflow is a drastic error on the high side. Overflow is a huge error. I mean to get a positive number, but I get a negative number instead. Underflow is one of those little things that's kind of insidious and tiny. It's not considered important. Overflow doesn't happen very often. When it does, it's obvious. Emperor has no clothing. Underflow happens on every floating point calculation, and it adds up. Bottom line is you never use a float unless there's no way around it. Float takes 8 bytes. It uses 8 bytes, and there was another one called real. that we don't use at all anymore, but if you see it, it's an old, ancient, archaic data type. We used to call them real. Floating point. Floating point has underflow. Integers have overflow. Character data. Character data, when we come up to character data, again, we're faced with two questions. Will we use only Western European characters? This isn't going to be easy to change later, so we have to think carefully. Or will we use the extended character sets? Are we going to need the Korean alphabet? Are we going to need the Japanese alphabet? Or will we only use the A, B, C, and D? It came as a shock to those of us in the United States that there were other alphabets, but they are there, and we have to consider them. So are we going to ever use those? And most of the time you are. Will our data piece be fixed length or of varying length? So will it be fixed? In other words, a Social Security number always has 9 digits. Or will it be a varying length like someone's name? Okay, let's look at the first one. Only Western European character sets. If it is a fixed length, we use char. If it's a variable length, we use varchar. If we have to go to other character sets besides the typical Western European sets, we will use nchar and nvarchar. Okay, nchar uses, instead of an 8-bit character, nchar uses a 16-bit character, and this gives us a whole nother world of characters that we can use. It takes up more byte, but nchar allocates 2 bytes per character. In this course's example, we see something like varchar 8 or something like that. In practice, if it's small, I suggest you use the char field instead of varchar. Varchar can save you a little bit of space, but it comes with an overhead, the cost of making it grow and shrink. And if all I'm going to be doing is saving a couple of bytes, that's just not worth the trouble. So if it's small, and I'm saying anything under 64, probably anything under 256 characters would be small. I would probably use a char, a fixed length size, if it were fairly small. Okay. Another issue we have with character data, null strings. One more, if a character field is null, then it has no value. The string, single quote, 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 this guy right here, 2 single quotes, is a value. It is the string that contains 0 character. If a field contains this, it is not null. It just doesn't have any characters in it. So we can have a string that has no characters in it. And then I talk about this constraint last name, so I can check that you must have a last name. Check that your last name is not null. But what if you have a last name, but it just doesn't have any characters in it? Next line, we'll check that the length of the string is not null. Constraint, last name 0, length. Check the length, len, and actually that's in the next chapter. Len, last name, is greater than 0. Nothing wrong with talking about it this time though. So check that the length, len, is greater than 0. Now, this matter will cause us a great deal of trouble in computing, that it's possible to have a name, but the name doesn't have any characters in it. And that problem is just really thorny for us in computer science. Dates and times. Point to keep in mind, database products will vary significantly. And Y2K was the death knell for the old date. In the old date and time video, this video actually goes into good detail on it. We just basically ran out of room. We used to store dates as character data. Excuse me just a moment. Okay, I'm back. We used to store dates as characters. We had 2 characters for the month, 2 characters that would be digits for the day, and 2 characters for the year. I think we stored the day first, actually, but therefore today's date would be stored as 07 for the month, 12 for the day, and 18 for the year. And that worked pretty well back in the 1960s. It would still be a long time before we hit the year 2000. And as we got closer and closer to it, people started getting more and more antsy about it. I can remember that very well. I remember hearing the word Y2K for the first time in like the 1980s. And I can remember somebody saying, you know, this is really going to be a problem when we get to the year 2000. But that was a long way off. Then I remember hearing talk about Y2K coming up a lot more in the 1990s. And as we approached that magical date, it became almost a crescendo. We were really talking about it then. And finally, we all did something about it. I guess everybody was hiding in bunkers and bought lots of ammunition and stuff like that. And nothing much happened. Well, we were all waiting there with our hand on the override switch and ready to take over manual control of anything that didn't work. Everything pretty well worked because we had put massive amounts of money into the problem. After that, we fixed the matter, and we fixed a point in time. Let's see if we've got it here. Fix a point in time and call that 0. And the 0 is Happy New Year of 1970 is time 0. That's the clock tick when it ticked over from 1969 to 1970. That was was the first second. So 0 was the Happy New Year. And our date time is an integer that records the number of clock ticks since that time. Next question is, what's a tick? Some clocks tick faster than others. The smaller the tick, the greater the accuracy. Or we might have a clock that ticks only once a year or something like that. So we will have a greater magnitude of the number if it's ticking very quickly. Database products use the date time. However, SQL Server had to rewrite that and call theirs date time too. Thus, date, if you just say date, it is a date only and it has no time value. It takes up 3 bytes. So that gives you the date. The time is the time of day, and that's usually 3 bytes. In SQL Server, we use the value datetime2, and that has a date and a time in it. So if you say it's a date time, that stores both a date and a time. If all you do is put a date in there, the time defaults to midnight. Questions? Let's see, data conversion, and it is 6:42. I think I'm going to put off data conversion until the next time. We're going to talk about data conversion. Let me briefly introduce it. Data conversion is that, all programming languages have a way to convert one data type to another. In fact, so for example, if I want to convert character data to integer, the question becomes then, what do I get? Well, if I convert a character to an integer, what I will get will be the ASCII code of that integer. For example, the ASCII code of capital A is a 65. So if I converted the character 65 to an integer, the character A, capital A, to an integer, I would get 65. We have a way to convert floating point to integer. If I do that, I typically chop off the decimal place. I have a way to convert integer into floating point, and it just picks up a decimal point of 0. And talk about that. I'm going to talk about this later. Data conversion, converting data from one data type to another. And since we're pretty close to the end of class for today, I'm going to stop there. And I don't think I have anybody here today. So given that you're not here, I'm going to go ahead and stop there. I'm going to begin on page 5, module 10, page 5, module 10, page 5 for Thursday. No, this is Thursday, isn't it? For next Tuesday. Um, and that will be July 17th. Very well. So thus, I'm going to end the recording for July 12th. And I hope somebody's actually watching these things. Good day now. I'm stopping the recording.